Alright kiddos, good morning to my favorite foursome. And you know that you really are my favorite foursome, else why in the world would I be up recording a video on chemistry of all things for anybody other than you guys at 7:15 in the morning. We're going to go ahead and continue on with stoichiometry. We are on page 171 and we're going to do problem on your own, problem number 6.3. And I'm thinking that once we get through this, once we're into the 1st of January and we have taken our second quarter exam, I'm thinking pizza party and movie night at somebody's house is an excellent idea. So Bree, that would be up to you to tell your mama that's what I want to do. So I have not looked at this since last night. Let's see if I can still remember what we're doing. It says citric acid, which is a component of fruit drinks, jams, and jellies, is produced using the following reaction. This is, let me see how far over here I can go. Way over. This is 6.3, page 170. We have C12, H22O11 plus H2O plus 3 oxygen, which yields citric acid to, what I'm going to do, I'm going to go ahead and erase this so that I don't run off the board so completely. C12, H22O11 plus water H2O plus 3 oxygen yields 2 citric acid, 2 C6 H8 O7 plus 4 water. Now let's make sure that our equation balances. 12 C's, 2 times 6 is 12 C's, 22H, 24H. 2 times 8 is 16. 22, 24. 2 times 8 is 16 plus 8 is 24 H's. 11, 12, 3 times 2 is 6. 12 plus 6 is 18 O's. So we have 2 times 7, 14 O's, plus 4 O's is 18. So our chemical equation is in balance. The question says, as a fruit drink manufacturer decides she needs 1.4 times 10 to the 5th moles of citric acid, 1.4 times 10 to the 5th moles of citric acid, what is the minimum amount of reactants that she will need? Minimum amount of reactants necessary. So we've got several things going on here that we're going to need to worry about. First off, we have citric acid here. And here we have reactant 1, reactant 2, and reactant 3, where we have this carbon compound reacting with water and additional oxygen to produce citric acid with still some leftover water. And we want to have 1.4 times 10 to the 5th moles of citric acid. What's the minimum amount of the reactants that are necessary? Now I'm thinking that if a chemist or a fruit drink manufacturer in this case is producing citric acid, they're not going to have the ability to measure in moles, so they're going to have to convert all of those moles into grams. So I want to go ahead and go back here to 6.4 and make sure that's what they're asking us to do. Nope. Not 6.4, it's 6.3. No, we don't have, since it hasn't specifically told us that we need to do this in grams, they're not requiring us to do that, which is a nice change. So this is a very basic stoichiometry problem. It's basic in that we're given a number of moles with which that we want to end up with. We have our balanced chemical equation. We don't have to worry about converting to grams or from kilograms and back and forth like this. We just have to see what our relationships are. The minimum amount of reactants means we're not going to worry about anything being in excess. We're going to assume that we have a perfectly functioning manufacturing process where all of our ingredients are used optimally. So let's go ahead and analyze this and see what we have. Remember, we're using these stoichiometric coefficients. I'm not sure we've even gotten to that word yet, but stoichiometric coefficients, they're just like algebraic coefficients. 3x, the algebraic coefficient is 3. A stoichiometric coefficient is the number that appears in front of the chemical chemical name of the compound. So we have a coefficient of 1, 1, 3, 2, and 4. Okay? This must be the marker that I didn't love a whole lot. Let's go back and see what we have. This tells us that 1 mole of this compound, which I don't know what it is, 1 mole of this will form 2 moles of citric acid. We have to have 1 mole of water to produce 2 moles of citric acid, and we have to have 3 moles of oxygen, and that will yield 2 moles of citric acid. So let's just say, I'm just going to, so we want to find out the minimum amount of each reactant. So for item 1, for reactant 1, the relationship between this is 1 mole of C12H22O11 yields 2 moles of citric acid. If we want to produce 1.4 times 10 to the 5th moles, 1.4 times 10 to the 5th moles of citric acid, how much of this particular compound here are we going to need? One mole of the compound produces 2 moles of citric acid. So you have compound to citric acid. Here we have compound to citric acid. This is the beauty of being able to do the equivalent fractions, so to speak, or doing cross multiplication. 1 times x, x is equal to 1.4 times 10 to the 5th, x times 2. So we have 2 times 1.4, 2.8, times 10 to the 5th moles of this compound. C12H22 011. Now that seems ridiculously easy. Let me verify. Okay, what did I do wrong? Probably said that, okay, this is citric acid. Ha 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 ha! Do you know what happens? Okay. Phooey. I'm going to go ahead and tell you that I got these upside down. We're relating the compound to citric acid, so this has to be compound to citric acid. I have my fraction over here turned upside down. Instead of going ahead and redoing the tape, taking the time to do that on a Sunday morning, I'm going to just say, make sure that you've got the right things in the right place. Sort of silly. So let me rewrite this in a way that will help me to avoid that problem in the future. I have 1 mole of compound. Reacts in the presence of water and oxygen to produce 2 moles citric acid. If we want to produce, according to our book, 1.4 times 10 to the 5th moles of citric acid, you have to have the citric acid at the same spot. 1.4 times 10 to the 5th moles of citric acid. How much of this compound are we going to have? So what we're going to have, 2x is equal to 1 times 1.4 times 10 to the 5th. And you'll see that in scientific notation we do use the x for multiplication, and that's a little confusing to you perhaps, because I have said, let's not use x, let's not use x, let's not use x for multiplication. And that's true, except in scientific notation. So we're just going to use the cursive x as the variable, the print x as multiplication here. Divide both sides of the equation by 2. You have x is equal to 1.4 times 10 to the 5th divided by 2. Now, when you divide 1.4 by 2, you have x is equal to 0.7 times 10 to the 5th. Now, can we use 0.7 times 10 to the 5th? Well, no, it's incorrect for 2 reasons. Well, first, the obvious one is the significant figures aren't correct. We need 2 significant figures. We only have 1 now. But even more importantly than that, it doesn't fit the formula for scientific notation. The numerical part of the scientific notation, I mean without the exponential, this part here has to be greater than 1 and less than 10. So 0.7 is not going to work. So this becomes x is equal to 7.0 times 10 to the minus 1. We have to convert 7.7 into scientific notation. If we multiply it by 10 to get 7.0, we're going to have to divide it by 10 or multiply by 1/10, which is 10 to the minus 1 times 10 to the 5th. So we end up with x being equal to 7.0 times 10 to the 4th moles of compound of the C12H22O11. Now, let me check my handy dandy little answer sheet here and make sure that this time I have solved it correctly. 7.0 times 10 to the 4th moles of C12H22O11. The arithmetic here is not particularly difficult. Dividing by 2, it's a little bit tricky if you're still struggling with scientific notation. It can be frustratingly annoying if you get your relationships turned upside down like I did the first time. But all in all, that's not difficult. So we have our first answer here. We have 7.0 times 10 to the 4th moles. 7.0 times 10 to the 4th moles C12H22O11. Now, let's see what we have next. It says we need the minimum number of reactants. That means of every single solitary thing here. Now, if we have the same relationship, look at this. 1 mole and 1 mole. So we have 1 mole of water is going to produce 2 moles of compound. I didn't even need to erase that compound, now did I? 1 mole of water. The calculations are the same. So we need 7.0 times 10 to the 4th moles of compound. We need 7.0 times 10 to the 4th moles of water as well. So isn't that the way that you like to be able to do some of your problems where the answer is already there? We also have 7.0 times 10 to the 4th moles of water. That's 7.0 times 10 to the 4th moles of water. Now, what about the oxygen? Because we have a coefficient of 3 here, different than 1. The ratio is going to be different, so we're going to have to set up a different relationship. We have 3 moles of oxygen will react to form 2 moles of citric acid, C6H7, H8, I guess they sound similar. 2 moles citric acid. Sir, okay. Citric acid. So, if we need to produce 1.4 times 10 to the 5th moles of citric acid, so we have 1.4 times 10 to the 5th moles of citric acid, how much oxygen do we need to have? How much oxygen? It's just going to be our variable of x. Going to cross multiply. And the citric acid is going to, the units of citric acid are going to cancel out, leaving us with only oxygen. 2 times x, 2x is equal to 3 times this, 3 times 1.4 times 10 to the 5th. And then, our next step, of course, to isolate x, we don't care about 2x, we care simply about x. So we are going to divide both sides of the equation by 2. 3 times 1.4 times 10 to the 5th divided by 2. X is going to be equal to, now let me do the 3.14. That's 3, 1.2, that's 4.2. 4.2 divided by 2 times 10 to the 5th. Look at this arithmetic and make sure that you're all right with it. 3 times 1.4, 3 times 4 is 12, 3 times 1 is 3, carry 1 is 4. Keep your decimal point. 4.2 divided by 2. When you cut 42 in half, you have 21. So this becomes 2.1 times 10 to the 5th moles oxygen. (2.1 times 10 to the 5th moles of oxygen. Look in our back, 2.1 times 10 to the 5th moles of oxygen. So your solution is, in order to make citric acid, these are the quantities of the 3 reactants that the manufacturer needs to have in one vat together so that they can react together in an optimum situation to produce the citric acid that we're looking for. So it's not hard. I mean, the actual mechanics of working these isn't hard at all. Where your challenge comes in is understanding the chemistry and translating it into English. And then once you understand what they're asking for, translating that into a mathematical or an algebraic sentence that you're able to solve properly. Okay, moving right on. Let's see what we have. Using chemical equations when limiting reactant is identified. One other way that chemists use stoichiometry is to determine the amount of products made when the limiting reactant is identified. For example, if a chemist wants to make silver chloride, which is used in photography, he might use the following reaction. This is on page 172. So we have Ag is silver. So we have Ag2CO3, which is a solid, plus hydrochloric acid. That's going to reduce to form silver chloride, AgCl plus water, probably oxygen, plus carbon dioxide. So the photographer needs to make silver chloride, which is used in the photo developing that he's going to do when he's not doing digital photography. So he has reactant number 1 and reactant number 2. And he wants to be able to be a good steward of the resources that God gives him, and he wants to not be wasteful as he is producing his silver chloride. So there's an optimum or an optimal way to produce these. Like you can say, you know, the minimum amount of this compound that you need to produce silver chloride, you use 1 mole of this to produce 2 of this. 1 mole of HCl to produce 2 of silver chloride. That assumes that the reaction is working perfectly, that there's no leftover anything. Sometimes though you want to put in extra when you are causing a chemical reaction, because you might have a big disparity or a large difference in the cost of things. Hydrochloric acid right here, it's pretty much dirt cheap. This silver containing compound here, on the other hand, is ridiculously expensive. So let's say that you put in 1 mole of this and 1 mole of hydrochloric acid, which you thought you had everything measured right. But for some reason you didn't have quite as much hydrochloric acid as you needed for the silver. Well, then all of your silver containing compound is not going to react. You're not going to get as much silver chloride as you could have had, and the cost of your silver chloride will increase, and you've not stewarded your resources well. So what you do is sometimes you add an excess. You add in more than you want. Like here, if we need 1 mole of hydrochloric acid, maybe you'd even add 1.5 moles of hydrochloric acid, because it costs like nothing to do. So you're not so much wasting as in the fact that you're ensuring that you don't waste the thing that's really, really expensive. It's like salt. When I'm measuring salt for my cookies or whatever, Bree may have noticed this, I know my kids have noticed it. Sometimes I'll pour the salt, pour salt into my hand, get the spoon or the half spoon, teaspoon, whatever I need, dump that in the recipe that I'm making, then I'll go over to the sink and just dump the salt out. Now, am I being wasteful of the salt? No, I'm not, because a whole canister, you know, the round tube of the round cylinder, 1 pound of salt cost me at Aldi about 35 cents. So the salt that I'm throwing away, that I'm letting dissolve in water and go down my drain, is a teeny tiny fraction of a penny. So it's much better to throw that salt down the drain than to pour here and go, ah! I have a tablespoon of salt in my cookies instead of a half teaspoon of salt, and then have to throw all of my cookie batch out. So that's the principle behind what we're doing here with limiting reactants. We have limiting reactants and we have excess reactants. Excess. If our hydrogen chloride is in excess, that means when the chemical reaction is completed, there's going to be some leftover HCl, but we don't care. That's what we want. We want to make certain that we have enough HCl so that that silver-containing compound will react completely. Okay, example 6.4, I'm going to let you go ahead and take the time to go through that on yourself. That's talking about, like right here. It says, if a chemist adds 5.61 moles of this compound to excess zinc, how much pure silver, which is Ag, can be made? It's telling you that if a chemist adds, well, like for here, let's just take this one instead of the chemical equation that we have in example 6.4. This is saying if the chemist adds 5.61 moles to excess hydrogen chloride, how much silver chloride is going to be formed? Well, that says that we have made sure that we have enough of this second compound for every bit of this first compound to react completely. So you see we have a relationship between these two compounds, 1 to 2. Let's just make it easy, we have 3 moles here of this silver-containing compound. How much silver chloride am I going to have? Well, we don't know. Remember, here we have the first compound, Ag2CO3. 1 mole of that reacts with 2 moles, reacts to form 2 moles of silver chloride. What happens if we have 3 moles of Ag2CO3 reacting with hydrogen chloride? How many moles of silver chloride will be found? We're going to have X is equal to 6 moles of silver chloride. Okay? Rate 1 to 2. In other words, your product is you're going to have twice as much product as you started with. If you start with 3, you're going to get 6. If you start with 1.4, you're going to get 2.8. You're going to have twice as much product as you did with the reactant to begin with. Okay, on your own problem, I want you guys to try 6.4 on your own. Let's go and look. I am on page 173. What we've been learning is that we try to determine how much reactant we need so that it will react fully with something else. Sometimes we want to see how much product we're going to get. Sometimes we're trying to figure out how much of the ingredients, how much of the starting material we need to have to begin with. Now this is when we're talking about stoichiometric coefficients. They provide a way of converting from the number of moles of one substance in the equation to the number of moles of any other substance in the equation. All that's saying is exactly what we've been doing. These numerical coefficients in front of the chemical names just gives us a ratio where we can come up with the number of moles of, here's reactant 1 and reactant 2. How much of reactant 1 do we need if we want to have 7 moles of reactant 2? That's all these stoichiometric coefficients are. This is just another classic stoichiometric. This is another excellent example of coming up with some coefficient, coming up with some big, long, fancy name to describe a really simple thing. It's vocabulary. All you have to do, stoichiometric coefficients, they're the numbers in front of the chemical formulas that you use to to create ratios. Then you can cross-multiply. Simple, simple, simple math. Cross-multiply to find your solutions. We're now on page 176. I'm sorry, it's 174. Volume relationships. Now what we've been doing, I don't even have to take time to do this. We've been having a solid plus a liquid plus maybe a gas plus maybe another solid to produce a solid plus a liquid. You know, we have 3 states of matter: solid, liquid, and gas. And matter can occur in any one of those states. Some types of matter, like water, H2O, occurs in all 3 states. Water can be a solid when it's light, when it's ice. Water can be a liquid when it's the way that we drink it. Water can occur as a gas when it's water vapor. Okay? We have seen the relationship between moles, which is really a measure of how you can take moles and convert to grams. There's this really fancy law. It only looks strange to us because we're not used to the French, but it's Gay-Lussac, and I haven't taken the time to, it's probably Lussac. Gay-Lussac. And his law is very valuable to us. Let me make, yeah. This says, the stoichiometric coefficients in a chemical equation relate the volumes of the gases in a chemical equation, as well as the number of moles. You have to know this. You have to be able to state this. Gay-Lussac's law. The stoichiometric coefficient, metric coefficients relate the volumes of the gases in a chemical equation as well as the moles. In a chemical equation as well as the number of moles. The way that this is valuable is there are some compounds, some elements that occur in their natural state as a gas. Oxygen, okay? Carbon dioxide, nitrogen, fluorine, chlorine, all of these occur in their natural state as a gas. So it's not going to be natural to say, give me 3 pounds of gas. So when I switched out my propane tank, I said I want 500 gallons of propane. Gallon is a unit of volume. I didn't say I want you to give me 250 pounds of propane. I said I want gallons of propane. So that would be liters. 500 gallons is a little bit more than gallon, a little bit more than 2,000 liters. So what Gay-Lussac, this French chemist, discovered a long time ago is that just like you use those stoichiometric coefficients, just like you can take that balanced chemical equation to relate the numbers of moles, to relate the moles of reactants and tell you how much the quantity of moles of product you get, you can also do that with volumes of gases. The kicker here is that you can only relate volumes of gases. You cannot relate, so you can go mole to mole, and you can go gas to gas, which is, I'm just going to put volume to volume. However, you cannot go back and forth from moles to volume. Okay, cannot do that. Let me draw a little X through this. Does not work. The units, if you will, have to stay the same. You can only do it if both the products are gases, if you're measuring volume and going to volume. Gay-Lussac's law. Okay. Here is an example. Example 6.5. An automobile engine burns gaseous octane, which is C8H18. If an automobile completely combusts 12 liters of gaseous octane in excess oxygen, how many liters of carbon dioxide will be produced? Okay, there's several things going on here that you have to recognize before you even begin to do your problem. First off, if an automobile completely combusts, is it a formation reaction, decomposition reaction, or combustion reaction? That's right. If it says it combusts, it's a combustion reaction. Now we can have a complete combustion reaction, you can have an incomplete combustion reaction, which is this. If an automobile completely combusts, so we have a complete combustion reaction. And what does your combustion reaction tell you? It tells you that you have a carbon. What time is it now?
7:20.
I'll have another good amount of time that I will be lecturing.
I have to be there at 8. At the latest.
I forgot about that you had to be there at 8. Go ahead and get ready and I'll finish up so
that you
can do that.
5 minutes ago and I overslept.
Okay. Complete combustion reaction means that you have a carbon compound, C8, H18 in this case is gaseous octane. When you have a complete combustion reaction, it's reacting in the presence of oxygen. So you cannot forget that you have oxygen. Now in this case, they didn't require you to remember that because it says it completely combusts 12 liters of octane in the presence of excess oxygen. So that tells you that we've got more than enough oxygen and reminds you that those two are relating together. How many liters of carbon dioxide will be produced? So you have to remember that when you have a complete combustion reaction, you have the carbon-containing compound reacts in the presence of oxygen to produce carbon dioxide, which is CO2, and water. Remember I said you've got to know incomplete combustion, combustion, formation, decomposition, reactions. This is why. Now, that was the first thing we had to notice, that we had the combustion reaction. Now, we have to make sure that our equation is balanced. We have 8 C's over here, and we have 1 C. So I'm going to rewrite this C8 H18 plus O2 produces, or yields, I'm just going to multiply by 8 so that my carbons match up. 8 CO2 plus water. Let's see what we have now. 8 C's, 8 C's. We have 18 H's. We have 2 H's. Let's multiply this by 9. Now we have 18 H's. Oh, good grief, I'm having a hard time getting this one balanced. Let's see. Now we have 8 times 2. We have 16 oxygen plus 9 oxygen. We have 25 oxygen. Bree, Laura, Matthew, this is why we're going to need to use fractional coefficients to balance this. You might be able to finagle this around until you come up and see here we've got an even number of oxygen on the right. I'm sorry, we have an odd number of oxygen. We have 25 oxygen molecules. Here we've got an even. So, you can either finagle around until you find your multiplier that will get you common multiples, or we can say 25 halves of O2. 25 halves O2. Let me make sure that's what I want to do. 2, 16, 18. Yes, that's exactly what it is. I want you to look at page 175 right now. In our book in example 5, they're not showing you this intermediate step here, and you're probably, very possibly going to look at the next step that they have and say, how in the world did they get it? The way they did that is by using our fractional coefficients here. Now, how do you clear an equation of fractions? You multiply by the denominator. The reason we did 25 halves divided by 2, multiplied by 2, 25 times 2 is 50, divided by 2 gives us 25. Then we have our 16 plus 9, which is 25 oxygen over here. Have to multiply both sides of this equation now by 2, which is going to produce for us, or is going to result in this equation 2 C8 H18 plus 25 O2 yielding 16 CO2 plus 18 H2O. Alright? Now it's balanced. 2 times 8 is 16. 16. 2 times 18, 36. 18 times 2 is 36. 25 times 2 is 50. We have 32 plus 18 is 50 oxygen. Alright? Now what do we need to do? This says, if an automobile completely combusts 12 liters of gaseous octane and excess hydrogen, how much carbon dioxide and water will be formed? Okay, we're going to combust 12 liters. How much carbon dioxide? Gaseous octane, gaseous oxygen, gaseous carbon dioxide. They're all three gases. So the relationship that we have here is 2 octane will produce 16 CO2, carbon dioxide. If we have 12 liters of octane, how much CO2 is going to be produced? 12 liters of octane, how much CO2? Are you ready to go?
Pretty much.
Okay, what time is it?
Okay.
Okay, so we have 2x is equal to 16 times 12. X is equal to 16 times 12 divided by 2, which is 8 times 12, which is going to give us 96 liters. 96 liters of carbon dioxide. Got several things going on here. Make sure that you understand your complete combustion reaction. Carbon compound reacts in the presence of oxygen, produces carbon dioxide and water. You have to come up with a balanced chemical equation. Because we have an odd number of oxygen atoms and an even number of oxygen atoms, we're using a fractional coefficient to bring us to a balanced equation. Balanced the equation just fine, however, you cannot have fractional coefficients in a final form of a chemical equation. So we multiplied both sides of that equation by 2 to give us this balanced chemical equation right here for the combustion of octane in the presence of excess oxygen. You have the relationship 2 moles of octane produce 16 moles of carbon dioxide. However, using Gay-Lussac's law, we saw that it doesn't have to only be moles. We can have that relationship when everything is a gas. So we have 2 liters, which is a volume measure, 2 liters of octane produce 16 liters of carbon dioxide. You set up your relationship. We could have reduced this to 1/8, but it was really not necessary. Cross multiply 2x is 16 times 12, divide by 2, we end up with 96 liters of octane. Let's see. Okay, on your own problem 6.5, do on your own. When I come back, I'm on page 176, mass relationships in chemical equations. Okay, I will see y'all shortly.